Hello students. In the previous videos, we have discussed about convolution sum and then the properties of convolution sum. Next, we took some examples taking a different kind of signals on convolution sum. Okay, and some examples were also given for you to try and get the solution for them using the methods that were used to solve the sums. Now, in this video, we will be discussing convolution integral. Okay, so this is the second method to represent an LTI system, and convolution integral mainly deals with continuous time signals. Okay, so convolution sum, we have from convolution sum, the general expression goes like this: k is equal to minus infinity to plus infinity x of k h of n minus k. Okay, so this is from convolution sum. Now, in case of convolution integral, we deal with continuous time signals. So, therefore, this summation will be replaced by integration, and the limit will be the same, varying from minus infinity to plus infinity. And since we are using integration, we use an integration variable tau. Okay, so considering all these aspects, let's start the convolution integral derivation. Now consider a continuous time signal x of t, which is expressed as a weighted superposition of time shifted impulses. Okay, so now we are considering a continuous time signal x of t as a weighted superposition of time shifted impulses. So that will look like this. I am directly writing the expression here. So integral of minus infinity to plus infinity x of tau. So tau represents the continuous variable which is used for integration, and delta t minus tau d tau. So call this as equation 1. So here the superposition is the integral instead of summation, and the time shifts are given by the variable tau here. Okay, so this weights x of tau d tau. So these are derived from the value of the signal x of t at time tau. So this x of tau d tau is derived from x of t only at time tau. Okay, so let's consider a system with system operator h, for which x of t is input, then y of t is the output. So then how do we define this? Y of t is equal to h of x of t. So we can express the output y of t in this manner as well. Let's substitute the value of x of t here. So then it will become h of integral minus infinity to plus infinity x of tau delta t minus tau d tau. Okay, so this is an LTI system. So that means it possesses both linearity and time invariance property. So first we using linearity property. So what we do, we are interchanging the integration with the operator h. That means we may change the order of the operator h and the integration. Okay, so using linearity property, we may change the order of operator h and integration. So then what happens to this expression? So we are interchanging this integration with the operator h. Then our equation will look like this. Y of t is equal to integral of minus infinity to plus infinity x of tau h of delta t minus tau d tau. So let's call this as equation 2. Okay. Now, since we have used the linearity property, second one is the time invariance property. So time invariance is whatever the time shift we apply in the input, the same time shift will reflect in the output as well. So considering this, so let's take the same thing once again. So we have a system. If we give delta t as an input, so you will get output h of t. That means the impulse response. Now, if the input itself is a time shifted one, then the output will also be a time shifted output. So that means we can express this h of t minus tau as, in terms of system operator, h of delta t minus tau. How do we get this? Because h of t we can express as h of delta t. Since the input is time shifted, then the output will also be time shifted one because of time invariance property. So I can write it because the system is time invariant. So this is just for your justification. So since the system is time invariant, then what happens to equation 2? Then y of t becomes integral of x of tau, and this term h of delta t minus tau. I'll replace this with h of t minus tau. So you can see we have h of delta t minus tau d tau here. So this term I forgot this. So h of delta t minus tau can be replaced by h of t minus tau. So that I am doing here, h of t minus tau d tau. Okay. So that this completes the derivation of convolution integral, and as we know that we represent convolution as with a symbol called star here. So that means y of t is denoted by x of t convolved with h of t, which means we have two functions to be convolved to obtain a third function. Here we are considering x of t as a static one and h of t as a time shifting one. Okay. So therefore we can write it like this: x of t convolved with h of t is equal to integral of minus infinity to plus infinity x of tau h of t minus tau d tau. So this or this, so both represents convolution integral expression. Okay. Hope you have understood this derivation. The steps are very similar to the convolution sum. So the only change is we are dealing with a continuous time signal, and instead of using summation, we use integration. And since we are using integration, the time shift will be denoted by the variable tau here. So this is the difference between convolution sum and convolution integral. Okay. If you have any queries, do reply me. Thank you for your time.